So I don't know how many people know the reason that we are all standing here and literally why we exist. It's because of a process called fusion. And the most obvious one of this is a star and our own sun. And how a star works is that it is essentially an enormous ball of hydrogen. It's so large that at the center of it, it becomes so hot, around 10 to 20 million degrees Celsius, and it has so much pressure that what it does is it forces the hydrogen nuclei to come together. This releases enormous amounts of energy. It's also the reason, literally, of what you are made out of. The elements that are in your body were primarily made in nucleosynthesis, which happens in the centers of stars. So Mother Nature, very important to listen to her. She's already told us the fusion is the power source of the universe. And look, now let's bring it down to Earth. We need clean energy and we need green energy, and we know this. And we've known it for quite a while, but we just had a very recent event, Hurricane Sandy, which brought it home very clearly and emphatically to the east coast of the United States. And even if perhaps we're not certain exactly what will happen with global climate change, I would just point to this picture in the lower left-hand corner of the Los Angeles basin. You just fly into any major United States city and you realize the price that we're paying for releasing hydrocarbons essentially without any control into the atmosphere. Okay, so now I'm going to bring it even more home. Let's think about Brookline. So here's our beloved Brookline. You see Chestnut Hill Reservoir. Maybe some of you go shop at Coolidge Corner afterwards, Jamaica Pond. So this is Brookline. And we think, well, what would it take? What's the kind of energy source that it would take to run Brookline? And it's really important to remember, without energy, we were seeing so many cool talks here at TEDx, lots of different ideas. You know what? If you don't have energy, you're not going to be able to do any of it. You must have energy to be able to accomplish all of these amazing things. So most of you think, well, let's think clean and green. One of the first ideas we have is solar power. And in fact, if you remember, here was my picture of the sun. We think solar power, great. So we go down to Earth and we ask ourselves, what would it take to run all of our lives? Transportation, heating, charging up your iPhone. So solar power is fantastic, but it has limitations, and it just comes from basic physical processes that it has a low amount of what we say is power density, namely that there's very small amounts of power that come per unit size or per unit area. And if you do a calculation, you can show that it takes a solar panel the size of Brookline to actually meet our power demands. And we don't want to cover up all of Brookline. And of course, it's only on when the sun is shining. This is not against solar power. I'm completely for solar power and its development. But nonetheless, we also know from the basic science of this is that it has limitations. It has its place, but it has limitations. So now what I'm going to do is explain why is that important. It's because the processes that occur, such as fusion in the interior of stars, have 100,000 to 1 million times the power density of solar. And what does that mean? That's kind of a hard number to sort of keep in your head. So I'm going to show you graphically about what this means. Instead of our solar panel covering up all of Brookline, let's think about what would happen if we were producing it by fusion energy instead. So we're going to go for a little ride on Google Maps. Come in closer, come in closer. You see where we're going actually. Oh, there's our star. And then in fact, there's Lincoln School, where we're all sitting right now. And if you go down, and please, when you go out of the building, you'll see that there's a small parking circle that in fact, a fusion device the size that would fit on the grass, which is outside the building right now, would be able to supply all energy demands for Brookline. So you see, you can understand, this has enormous possibilities. And in fact, that is what I work on. And we call this magnetic fusion, and I'll explain about why it's called that. But it is, think of it, bringing a star to Earth. And the idea is that, in fact, we would engineer and construct such a device, which I'm showing here, that literally would fit, in fact, on the grass, which is outside. So we go back. Fusion is this power source. And how does it work? So the reason that it's so different is because a fundamental aspect of nature, of how we all are put together, is that atoms have almost all of their mass in an extremely small nucleus, which is at the center of the atom. And when you rearrange those nuclei, the amount of energy that comes out is millions of times larger than when you rearrange atoms, which is what you're doing when you're, say, burning coal. And on Earth, what we do is we take two special forms, heavy forms of hydrogen, essentially smash them together, fairly high energy, but when they come together, they form another nucleus that rearranges itself, and it releases something like 1,000 times the amount of energy that it was required to actually get them to go together. And it's this process by which we would, in fact, get our net energy out. And this is the process that happens in the interior of stars. So, I know, everybody heard the N word, the nuclear word. I'm not so sure about this, because I know that there are issues with this. And here's one of the things you might worry about, like all this crazy fuel that you're talking about. Isn't it going to be bad for the environment to extract this fuel? Well, this is probably the greatest lure of fusion energy. The fuel is so abundant because it is essentially hydrogen. It actually occurs naturally in seawater, and it's effectively unlimited to all people on Earth. And the example that we put forward here is that if I extracted a very small portion of, and in fact harvested these heavy forms of hydrogen from the top inch of Boston Harbor, so we all know how big Boston Harbor is, the top inch of Boston Harbor, this would supply all of Boston's electricity demands for about 100 years. That's how incredibly intense the energy source is. And you get it from natural seawater. Also, it doesn't happen to be just where you happen to be on the planet. Everybody would have access to the fuel. So the other thing, which is a concern with nuclear energy, which most people hear, is this: well, I'm worried about the waste, because you're going to have dangerous waste which will be around for millennia. So this is the other aspect of fusion, is that in fact the fusion reaction itself produces helium. So I'd say let's blow up some kids' balloons and have a party. It's not quite as simple as that, and I'll explain that in a slide that comes up a little later, but nonetheless, the inherent, what we say, nuclear fuel cycle ends in helium, as it does in stars, by the way. That's why stars die eventually, and they will not fuse anymore. And then, is it safe? Is it going to blow up like a bomb? We worry about this. Is it going to be safe? Well, in fact, and this sounds counterintuitive, but fusion requires temperatures which are around 100 million degrees. That actually sounds dangerous, but it's the opposite, because that's what happens in the center of stars. But when we bring this to Earth, it means that the fusion instantly turns off the moment it sees anything to do about the outside world, like our terrestrial world. It just instantly turns itself off. In fact, it's hard to keep it going in some sense. So in fact, you're saying, well, now, like, how can you do this? Because you just said it can't work on Earth. Well, it can't work directly on Earth, and this is where magnetic fusion comes in, is that the interior of stars are so hot that the constituent atoms have actually literally been ripped apart. And the electrons, which are part of the atom, have been pulled off, and so now all you have are charged particles. And a fundamental force in nature is that when a particle has a charge and you have a magnetic field, they combine together, and that magnetic field effectively holds that charged particle in place. And that's what we do on Earth. And here's a cartoon of this, is that we take these lines that you're seeing going around are in fact magnetic field lines, and they hold this medium and essentially suspend it in midair. In fact, it's not even in air, it's in a vacuum, away from any physical object. And by the way that the science of this works is that the stronger the magnetic field is, the more it will hold that medium, which we call a plasma, which is why I work at a plasma science center, is that it holds it and insulates it better. And in the end, what you do is, in fact, engineer and design this magnetic field. This magnetic field is roughly 100,000 times the Earth's magnetic field. Very, very strong. So how do you make those? You engineer large sets of coils, which are demonstrated over here on the right, and then you twist it around into the shape of a donut, because a donut is a closed geometry, and then therefore basically the plasma cannot escape, and you can make it get very hot indeed. So MIT has in fact been the pioneer of this fusion of what we say ultra-high magnetic field strength. And this is in fact the device at MIT. It's in Cambridge on the MIT campus. The orange ring that you see in the center of this is in fact the plasma. I can almost fit my arms around it. It's about this big. And then the surrounding structure produces extremely high magnetic fields and basically holds this in place. And so you might not know this, but in fact in Cambridge, fairly routinely, we actually create these. This is not science fiction. We make these plasmas, and this small device in the center that I could almost put my hand into achieves 100 million degrees. It also is around 3 atmospheres of pressure, but there's a limitation, namely that with this device, to make these magnetic fields, we use very large copper wires, and these wires will become too hot if we tried to run it continuously, so we intentionally only run it for a few seconds. So how do we make this an energy source? Well, how we make it an energy source comes about from what I would almost call a miracle of nature. It's called superconductors. Superconductors are particular kinds of material that when you pass electrical current through them, it does not heat, it does not lose any of the electricity. You're most familiar with this is in MRI devices. MRI devices make this high magnetic field that allows you to image inside the body. We take it up another whole other level, is that we try to make magnetic fields which are 3 to 4 times even the strength of those large magnetic fields, because the stronger we make the magnetic field, then the smaller we can make the device and the more attractive it looks like as an energy source. So this is in fact, and TED is about this, about synergies and things that happen. Within the last 5 to 10 years, because of the desire to be able to transmit electricity from sources to your home with minimal losses, you can use such superconducting tapes. And what is amazing is that what we have discovered, and in fact what I'm showing you is the result of a design study that was done mostly by my students at MIT, in fact, is that we realized this could have a synergistic role, in fact, propelling fusion forward, because the size of the magnetic field could roughly be doubled, even though you don't have to pay a price in electricity, and that means we could actually get a working fusion power plant that, in fact, would basically sit on that piece of grass outside, and you can see the man beside it. The other interesting one was that we also realized, because it was superconducting tape, we could actually unlock the magnetic fields, which I'm showing in a cartoon, and the thing that you see in the middle, which has the yellow pointed around it, is effectively the entire replaceable component. Everything else you can use for up to 30 years or more, we're not exactly sure how long, and that would provide electricity 24 hours a day at a level which is around 250 million watts of electricity. That would in fact be enough to supply Brookline with its energy demands 24/7. So we're very excited about this, and this makes it even more ironic that our lab is about to close. In fact, the federal government is threatening to remove all of our funding, and it will in fact cut off this extremely promising area of research towards this energy source. And I would urge you, and I cannot go through all the details in this period of time, but fusionfuture.org, or anything about MIT and fusion, and you'll be able to educate yourself if you're interested. So I just want to, again, as you walk out of the school, think about this, is that, energy, very important. All hands on deck. We need energy sources which are clean and reliable. And please think about fusion, and hopefully this will get you more interested. Thank you very much.